This is our second video on laws of thermodynamics, and I'm gonna start with the introduction to Carnot engine. And a Carnot engine is an ideal engine whose working is perfectly irreversible. So this engine uses an ideal gas as a working substance and performs four-stroke process to complete one cycle. And like in this example on the left picture, you see that there are two temperatures, T1 or T cold and T hot. And there are two isothermal processes. They are in red because the temperature stays the same. So this one is isothermal. And so is this part isothermal. So when the volume is, when the pressure is decreasing and the volume is increasing, the heat is added into the system. So here you see the heat is added into the system to keep that same temperature. And here you have to spill that heat in order to keep that temperature because the pressure is increasing between this point and this point. So let's call the points 1, 2, 3, and 4. And so this ideal engine is operating between two given temperatures and has the greatest possible efficiency of any heat engine operating between these two temperatures. And all engines employing only reversible processes have this same maximum efficiency when operating between the same given temperatures. The two red ones are isothermal processes and two blue ones adiabatic processes. So in adiabatic process, there is no heat added or taken into the system. So the change of heat here is equal to 0, and the change of heat on this side is also equal to 0. So Carnot engine is the imaginary engine. It has the highest efficiency possible between two given temperatures, as is shown in the picture. So there is no real engine that will give you the same efficiency. So it is a reversible engine, but all real engines are irreversible, and the actual efficiency of the engine can never be as great as the Carnot engine. On the right side on the right side picture represents the engine. So you have the high temperature, the source of the heat, and then you have lower temperature, T cold, and this is where the heat sinks after it wasn't used. And in between you have the work is done. So the efficiency of an engine is equal to the work done by the engine on the surrounding over the heat entering the system. There's a few formulas that you can use for efficiency. You can also say that it is 1 over heat cold over heat going into the hot, coming from the hot reservoir. It's actually, the work is done is this one, the hot minus cold over Q hot. So this is where this second formula comes from. So the work is, so if there's so much heat is coming and some of it is going to be thrown into the work, the rest is going down and spills into the sink. So you could use the second formula. And another one for efficiency, it is 1 minus T cold over T hot. And it's the same derivation where you have the hot temperature minus the cold temperature divided by the hot temperature. Let's look at some questions, and some of them will be involved with the work done, engines, and others will be, or efficiency, and some will be just the laws of thermodynamics. So here they say, suppose you have 60 meter cubic of ideal gas and the pressure is 20 Pascal to a volume of 120 meter cubic. So you have the volume is changing and the pressure stays constant. So how much work does the gas do? And when they mean the gas do, the gas does on the environment. So there is expansion, so the work on the gas is negative, but the work done on the environment is positive. So the work is equal to P delta V, and the pressure is 200 Pascal, and the change of the volume is 60. So that gives me 12,000 joules of energy, and it is positive work on the environment, negative work for the gas. In this question, they say, suppose you have a mole of helium to play around with on a rainy day of a temperature 20 degrees Celsius, and for fun you decide to expand isothermally, so temperature stays the same, it from V sub 0 initial equals to 0.01 meter cubic to final volume of 0.02 meter cubic. What is the work done by the gas in the expansion? If you remember from the laws of thermodynamics, the work in isothermal process is equal to nRT, and then you have the natural log of the final volume over the initial volume. So if I plug in my numbers, you have a 1 mole of gas, and the gas constant is 8.3, and the temperature is 20 degrees Celsius. I have to convert it into Kelvin, so that is 273 plus 20 gives me 293, and then I have the natural log of the final volume, 0.02, divided by initial volume, and that will give me 1.690 joules. You don't have to remember this formula. I have not seen an AP exam asking to use this formula, and if they do, they don't give you the formula, so you would have to they will give you in the problem, not on the formula sheets. So the previous formula for thermodynamics, the work done in isothermal process, you don't have to memorize it for AP exam, but for our lessons you will see it from time to time, so you just have to know where to get it and how to use it. And in this question, they say that, I had to open the rest of the question. They say that by visual inspection, order the PV diagram shown in from the most negative work done on the system to the most positive work done on the system. So from the lowest work done on the system to the most work done on the system. So I know that in PV diagrams, the work done on the gas or by the gas is the area underneath. So for the first one, I have this one is in atmospheric pressures and meter cubic. So I have 1 by 2, so that is 2, and then I have 1/2 the height, which is 1, and times the base, which is 2, so that is also 2. So 2 and 2 gives me 4, and it is 10 to the 5th joules. But I have to think whether it is positive or negative work. And in this case, I see that the gas expanded. And when the gas is expanding, this is the negative work on the gas. So the gas did the work on the environment. Positive work on the environment, negative work on the gas. So for the next question, we're going to do the same. We're going to look at the area underneath. So for this question, I have 1 by 1, so that's 1. And here I have 1 by 2, so that's 2. 1 and 2 gives me 3, and it is 10 to the 5th joules. And then now I have to think about the sign. So here I am compressing the gas. So because I'm compressing the gas, the work is done positive. For the next one, expanding the gas. So positive work on the environment, negative work on the gas. So I know it's negative. Then I have 1 by 2, which is 2. And then for the next one, it is 1 by 1. It's 1/2 of the height times the base, 1 by 1. So 2 and 1 gives me 3. And again, 10 to the 5th joules. And for the last one, it is compressing again. When I'm compressing, the sign is positive on the gas, negative on the environment, because the environment does the work on the gas to increase the energy of the gas. And here I have 2 by 2. So that is 4 10 to the 5th joules. And I have to place them from the most negative to the most positive. So I have most negative is A, then C, or actually they have it in letters. So it's 1, then it is 3, then it is 2, and then it is 4. And that would be 1, 3, 2, 4. It's B. In this question, they say an ideal gas absorbs 5,000 joules of energy while doing 2,000 joules of work on the environment during a constant pressure process. Compute the change in the internal energy of the gas. So internal energy of the gas, delta U, is equal to 3/2 nRT, but it also equals to the heat into or out of the system plus minus, so it could be positive or negative, and plus minus the work done on the system or by the system. So the internal energy is equal to, it absorbed 5,000 joules of energy, so 5,000 joules of energy was added into the system, but it did 2,000 work on the environment, so minus 2,000 joules on the environment. So that gives me 3,000 joules of energy is gained by the gas. Then for the next question, they say if the internal energy now drops by 4.5 or 4,500 joules and 2,000 joules is expelled from the system, find the change in the volume assuming a constant pressure process, and they give you the pressure doesn't change. So they say the internal energy now decreased by 4,500 joules, so it drops by 4,500 joules, and then 7,500 joules is expelled from the system, so 7,500 joules expelled from the system. And find the change in the volume assuming the constant pressure. So the work is equal to pressure, and you have change of the volume, and the volume does not change. So you have negative, or the gas is losing the energy, heat is dropped and or taken out of the system, and then the volume changes, but the pressure stays the same. And because the pressure staying the same, I know that there was positive work done on the gas, so the volume decreased, not increased. So I'm gonna plug in positive sign over here. Now I have the pressure, which is 10 to the 5th times change of the volume is equal to 3,000. And if I divide both sides by 10 to the 5th, then the volume, change of the volume is equal to 0.03 meter cubic. In this question, they say suppose a system of monatomic ideal gas, 210 to the 5th Pascal, and initial temperature of 293 Kelvin slowly expands at constant pressure from a volume of 1 liter to 2.5 liters, and liter stands for 10 to negative 3 meter cubic. Find the work done on the environment find the change in internal energy of the gas and use the first law of thermodynamics to obtain the thermal energy absorbed by the gas during this process. So the work done on the gas, is equal to P delta V, and the pressure is at 2 pascals, and it's a constant pressure, so I have 2 10 to the 5th, and change of the volume is 2.5 minus 1 and 10 to the negative 3 because it's liters. And so it is the expansion, and I have the work is equal to 310 to the second joules. And I know that the work is done, the gas in this case is negative because there is expansion, so the work is done negative. But because there's kept constant pressure, I know that heat must be added into the system. So find the change in internal energy of the gas, or delta U. And delta U is equal to 3/2 nRT. And I know that nRT is equal to P delta V. So I have 3/2 P delta V. So that gives me 3/2. The pressure is 210 to the 5th, and the change of the volume is 2.5 minus 1.5, 10 to negative 3. So that is 1.5, 10 to the negative 3. So delta U is equal to, or the change of internal energy of the gas is equal to 2 and 2 can be cancelled, and I have 4.5 10 to the second joules. And so I know by how much the energy changed. So now I'm going to use the first law of thermodynamics, where I have delta U is equal to Q plus minus the work done. Delta U, or internal energy of the gas, is 450, the one that we just found, and equals to the heat added into the system. I know it was added into the system because the gas is expanding, but the pressure is kept constant, and the work was done negative 300. So from here I can see that the heat that was added is equal to 750 joules. So they added 750 joules of energy to expand the gas, but not to lose pressure. Here's a multiple choice question, and in this question they ask you the process depicted in PV diagram shows as an isothermal one. What is represented by the shaded area below the curve? I'll let you think for a second or pause it. So if you did pause it and now unpaused it, I hope you chose A, because the shaded area underneath the PV diagram represents work. In the next question, a gas is to be compressed from 3 to 1 meter cubic. Which is harder, compressing isothermally or adiabatically? And go ahead and pause it and think about it and choose your solution or the answer. And if you're back, then I hope again you chose isothermally, because isothermal process requires more work compared to adiabatic, because it has to be keeping the engine at the same temperature. In the next question, they say, what is the pressure inside of 32 10 to the negative 3 meter cubic container holding 85 kilogram of argon gas? Molecular mass is 40 gram and at the temperature of 20 degrees Celsius. So I can say that PV is equal to nRT. So P1 V1 is equal to nRT1, and N is the mass of the gas over molecular mass, and then I have RT. We're looking for the pressure, so I'm gonna say pressure and the volume is given 32 10 to the negative 3, and the mass is 85 kilogram, and the molar mass is 0.04 kilogram. I have to convert gram into kilogram. R is 8.3, and the temperature is 20 degrees Celsius, which is 293 Kelvin. So the pressure is going to be equal to 1615 atmospheric pressure, or 10 to the 5th power. In this question, they say 2 mole of gas are in a container whose volume can be adjusted with a movable piston. When the volume is 3.2 liters, or 10 to negative 3 meter cubic, the temperature is 30 degrees Celsius. With constant pressure remained, heat is added to the gas, and the piston is allowed to move until the volume is 5 liters. Find the final temperature. So because the gas is expanding, it keeps the same pressure. So with the same pressure, I can use the ideal gas equation, where I have P1 V1 over T1 is equal to P2 V2 over T2. But I also have P1 V1 is equal to nR T1. So I can find what my pressure 1 is equal to. So I have P1, and the volume is 3.2 10 to the negative 3, 3.2 10 to the negative 3, 2 mole of the gas, 8.3, and the temperature is 30 degrees Celsius, which is 303 Kelvin. So from here, I can see that pressure 1 is equal to 15,718 10 to the power of 2 pascals, or it equals to 15.72 atmospheric pressure. Because they say the pressure stays the constant, I can actually cancel it. You didn't even need that part. So I have V1 is 3.2 10 to the negative 3, and the temperature is 303, and V2 is 5 liters, so 5 10 to the negative 3, and I'm looking for the second temperature. So cross multiply, and I'm gonna get T2 is equal to 473.4 Kelvin. That is about 200 degrees Celsius. So the temperature increases from 30 to 200 degrees Celsius. In this problem, they say in a car engine operating at 1.8 10 to the third revolutions per minute, the expansion of hot, high-pressure gas against a piston occurs in about 10 milliseconds. Because energy transfer by heat typically takes a time on the order of minutes or hours, it is safe to assume that little energy leaves the hot gas during the expansion. Estimate the work done by the gas on the piston during this adiabatic process, because they said no energy leaves the system, so it is adiabatic process, by assuming the engine cylinder containing 1.1 moles of ideal gas, and which goes from 1200 Kelvin to 400 Kelvin. So it looks like the temperature drops. Typical engine temperatures during the expansion. So by the first law of thermodynamics, we have the internal energy of the gas depends on the heat added into the system and plus minus the work done on the system or by the system. And because the change of the heat in the system is equal to 0, I can write that internal energy of the gas is actually equal to the positive negative work done on the system or by the system. So from here, in order to calculate the work done by the gas on the piston, I can say that delta U is 3/2 and R delta T. So that's 3/2 and R delta T, and that is equal to work. So I can plug in the numbers, and I have the work is equal to negative 996 joules. So it is a negative work done on the gas or by the gas. Actually, on the gas, the negative work is 900-6, but engine did, or piston rose, so piston got some energy from the gas, so the work done on the piston by the gas is 996 joules positive. So again, depending on how the question is asked, and because they say what the work was done on the piston, not on the gas, so on the gas the work is energy, but on the piston the work is positive. In this question, they say how much thermal energy must be added to 5 moles of monatomic ideal gas at 300 Kelvin and with a constant volume of 1.5 liters or 1.5 10 to negative 3 meter cubic in order to raise the temperature from of the gas by 380 Kelvin. So again, from the first law of thermodynamics, I have delta U is equal to heat plus minus the work done on the gas. And because the volume is kept constant, so there's no work, so the work is equal to 0 because the change of the volume is equal to 0. And therefore, I have internal energy is equal to the heat added into the system. So the question is how much thermal energy must be added into the system. So I can say heat is equal to 3/2 because the internal energy is equal to 3/2. And then I have N R delta T. So it's 3/2 and N is 5, R is 8.3, the ideal gas constant, and the temperature changes by 80 degrees Kelvin. So I have 80 Kelvin. So the heat that had to be added into the system is equal to 4980 joules. I will stop our video on laws of thermodynamics 2 at this point, and thank you for watching this one, and I'll see you in the next one where we're going to do more PV diagram practices, and probably I hope we're going to get through some of the efficiency problems in the next video, video 3 for laws of thermodynamics. So thank you for watching. I'll see you in the next video.